All right, everybody, welcome back to our summer school, and it's our second day, and Federico is continuing his lectures on calibrated manifolds.
Thank you very much. What I will be talking about today is non-compact complete manifolds of exceptional holonomy. But first, let me tell you what previously was on the screens last day. What I told you yesterday was that given a Riemannian manifold, we can associate a subgroup of SON, and the only possible elements of the only possible subgroups of SON that can appear are in Berger's list. So it's either SON, UM, SUM, SPM, SPM times SP1, G2, SP7. And I told you that G2 and SP7 are somehow special because they don't come in family, are just in dimension 7 and 8. So I also told you that using the so-called holonomy principle for G2 and SP7 manifolds are characterized by closed forms that are phi and star phi in dimension that are three forms and four forms respectively in the G2 case, and the fourth form in the spin7 case. So a priori, Berger list originally included more Lie subgroups of SON. Indeed, spin9 was also in the list, but it turns out, due to the work of Fernandez and Gray and Alexevsky, I think, that it must be a symmetric space. So a priori, G2 and spin7 could also not appear really in the list, so they could a priori, we don't know. We don't know yet whether there are. I mean, now we do know, but we didn't know until very recently whether or not there are manifolds with holonomy G2 and spin7. So indeed, as I mentioned, Berger said that G2 and spin7 can appear as holonomy of some Riemannian manifold, but only due to the work of Robert Bryan in 1984, we found the first incomplete matrix with holonomy G2 and spin7. And the idea behind this proof was using Cartan-Kähler for overdetermined PDEs. So this is a bit of the history of the field, and later, Bryan and Salomon in 1989, they constructed the first complete examples, and these are done on S3 times R4, the anti-self dual 2 forms over S4, and the anti-self dual 2 forms over CP2 in the G2 case, and the negative spinor bundle over S4 in the spin7 case. So today, the first half of the talk is going to be a description of the Bryan and Salomon manifolds in each of these cases here. But first, let me finish the history of manifolds with holonomy G2 and spin7. So in 1995, 1996, Joyce constructed the first compact examples, and his idea was to use a generalized Kummer construction. So he picked a 7-dimensional torus with some involution, and this involution created some orbifold singularities that he resolved by gluing in some hyperkähler for manifolds time flat T3s. The following example of G2 manifolds that we know is due to Kovalev, Coty, Hastings, Norton, and Pacini, and they constructed more examples by the so-called twisted connected sum construction that I'm not going to recall. Later, Joyce and Karagiannis in 2006 improved the generalized Kummer construction, and later the Foscolo, Haskin, and Nordstrom in 2021 produced more examples of complete non-compact G2 manifolds. And their idea was to take a circle bundle over an asymptotic Calabi-Yau threefolds, and they managed to construct a one-parameter family near the collapse limit of the Calabi-Yau. But even more importantly for the scope of this mini course, once again, Foscolo, Haskin, and Nordstrom in 21, they classified all complete non-compact SU2 square times U1 invariant G2 manifolds, and their construction uses a cohomogeneity 1 technique. And this is going to be essentially the second bulk of today's lecture. So if today is not really research in the sense that it's not it's still quite new, the things that I'm going to talk about today. And finally, the last piece of examples that I want to mention is Foscolo in 2021. He constructed more examples of complete spin 7 manifolds from asymptotically conical G2 orbifolds. Okay, so this was just a very brief history of, and it's not complete, of course, but it's a bit of a history of complete compact and non-compact G2 manifolds and spin 7 manifolds that have been constructed in the last 30 years, 40 years. Okay, if there are no questions about the history of G2 and spin 7 manifolds, I will start by talking a little bit about the G2 Bryan and Salomon metrics on S3 times R4. So the setup is, okay, we have an S3 which we induce, which we endow with the metric of constant sectional curvature 2. The 2 is just because it made my computation easier. And R4, it's just endowed with a standard Euclidean structure. So we have a nice product metric on S3 times R4. Now, we are going to construct so-called horizontal and vertical one forms. And the idea is that if I have a local orthonormal frame of S3, then I also have a local orthonormal coframe by just taking the dual basis. And this is a local coframe on our, so this should be an S3, sorry, of our sphere. And given this data, we have a Levi-Città connection matrix. So this is the matrix which satisfies this equation here. So essentially, the connection matrix is a matrix that encodes all the covariant derivatives of a Levi-Città connection. And this is characterized by the first structure equation, which is this formula here. Now, in the context that we will be working on, we know that S3 is diffeomorphic to SP1. So it's just the unit quaternions in H. And so being SP1 a Lie group, it is parallelizable by left invariant vector fields, E1, E2, and E3, which we assume to satisfy the condition EIJ equal to -2 EK. And so in particular, this implies that our coframe satisfies the equation dBi equal to 2 BJBK, where IJK is going to be a cyclic permutation of 1, 2, 3. So if IJK is going to be 1, 2, 3, or 2, 3, 1, or 3, 1, 2. So given this equation here, dBi equal to 2 BJ wedge BK, you can check that using the first structure equation, that the rho i's are going to be equal to -1/2 beacon I in this context. Now, because of this form, so because of this example here, all the forms that we are going to construct will be globally defined because we have a globally defined coframe. So this is going to be evident and apparent in the following. But now we have dealt with the S3 part of our manifold. Now we just look at R4, and R4 we parameterize it by A0, A1, A2, A3, just the names of the coordinates of R4, and we consider S3 times R4 as the trivial vector bundle over S3. So in this small picture here, I have U, that is my coordinate patch of S3, and I have my vector field C1, E2, E3 here that are my frame. And at each point of view, we have R4, which is parameterized by A. Now, we need, since we are considering a vector bundle over S3, which is, well, trivial, but it's a vector bundle nonetheless, then we can essentially do the same thing and endow S3 times R4 with a connection. And this time we choose the connection matrix to have this form here. So the row 1, row 2, and row 3 are the components of the Levi-Civita connection of S3. Now, you might ask, why are we considering a connection like this one? And the reason is, if you know a little bit of spin geometry, then you'll realize that rho is the spin connection on the spin bundle over S3, which is a trivial bundle over S3. So I'm just, alternatively, I could have told you just take the spinor bundle over S3 with its natural spin connection, and everything would follow in the exact same way. Okay, so now I can define in the usual way the vertical one forms and the horizontal one forms. So the vertical one forms with respect to this connection are given by the A plus A dot rho, where rho is the connection matrix here. And if you do the computation, then you see that C naught is equal to the A0 plus A1 rho 1, A2 rho 2 plus A3 rho 3. And C1 is equal to dA1 minus A0 rho 1 minus A2 rho 3 plus A3 rho 2. And similarly, you can see how what is the form of C2 and C3. And the horizontal one forms on the other end are just going to be the pullback of the B1, B2, B3 that of the coframe that I have defined on S3. And from now on, we will omit the P star because this is just going to be annoying. Okay, so I given you, I've told you let's speak S3 and let's speak R4, and now we have constructed these one forms C0, C1, C2, C3, and B1, B2, B3 on our S3 times R4. How can we construct from such one forms a G2 structure? So the idea is that if I pick R squared to be the distance from the zero section, so A0 squared plus A1 squared plus A2 squared plus A3 squared, then I can define my G2 structure as U cube B1, B2, B3, where U is just a function of R squared plus UV squared, sum over I of BI wedge omega I, where omega I are the anti-self-dual two forms given by the vertical one forms. So in other words, what we are doing here is, so I told you that you can remember the form of phi as being R3 plus R4 with, and then write R3 plus R4 in as the volume of the first R3 plus sum over I, dxi wedge omega I. And the idea is essentially that the role of R3 is played by the horizontal one forms in this case, and the role of R4 is played by the vertical one forms. And we also have to pick U and V to be functions of R square, and these functions of R square are explicitly given by these formulas here, but a way to remember them is by knowing that they satisfy this system of ODEs. Now, given such a G2 structure, we automatically get a metric and a Hodge star. And you can see here that the metric is precisely a conformal change of the metric on the horizontal space plus the a conformal change of the metric on the vertical space. So I will come back to this again and again for all the Bryan-Salomon manifolds, because this is essentially the idea. Okay, so given such a DC, then Bryan and Salomon, what they've proven was that S3 times R4 is a complete manifold with holonomy equal to G2, and the G2 structure is invariant under the action of Q1, Q2 of SE2 cube acting in this way. So it means that Q1 acts on the first factor on the left, Q2 acts on the second factor on the left, and Q3 acts diagonally by the right. So here I'm identifying SU2 with SP1, so with a unit quaternions. Any questions on the S3 times R4 Bryan and Salomon construction? Okay, so if not, we can briefly see the proof of this fact. It's just a long computation, but I will just go through it very quickly so that you can check all the other cases on your own as an exercise. So we will only prove that phi is closed and co-closed, so it's a torsion-free G2 structure, and we will prove that the metric is complete. What is left would be to show that the holonomy group is equal to G2, but this can be done by using Bryan's theorem, one of Bryan's theorem, and you can see that on the original paper of Bryan and Salomon. So we want to compute the derivative of this term here, of this G2 structure. So we first deal with this term and this term. So B1 wedge B2 wedge B3 plus sum over I BI wedge omega I. So if we take B1, B2, and B3 as in the example, so to be the left invariant one forms, then the exterior derivative of BI is equal to 2 times BJ wedge BK. And so it is clear that if we take the derivative of the volume form, we get 0. And we can use the structure equations that we talked about before to compute them. So we know that the rho i's are equal to the bi's, and so we can compute dxc0, dxc1, and dxc2, and dxc3 explicitly. And this is the formula that you get. So here I'm just with this xi in red, it just means that vi can be actually written as xi because the additional terms vanish. And well, another straightforward computation tell us that 1/2 dr squared, which is rdr, can also be written as a0 xc0 plus a1 xc1 plus a2 xc2 plus a3 xc3. So now, given these two observations here, if we compute b1 wedge d omega 1, you can check, it's pretty straightforward, that what you get is b1 wedge b2 wedge omega 3 plus b3 wedge b1 wedge omega 2 plus rdr wedge the volume of a sphere. And similarly, then bi wedge d omega I is equal to bi wedge bj wedge omega k plus bk wedge bi wedge omega j plus rdr wedge the volume of a sphere. So here is really just a straightforward computation as the one in the previous slide. And now, since we know how d of bi, since we know that d of bi is equal to twice bj bk, then the second formula here follows, is directly coming from the first one. And you can check now that the first term cancels out with the second and the third one if we take the sum over all the possible i's, and the only remaining term is the last one with a factor of 3. So to just sum up, if we take the derivative of my phi c, then I have to take the derivative in r of u to a third, u cube, and the term will come with a derivative of 2r dr wedge the volume of a sphere. Then the term involving the derivative of the volume of a sphere is going to vanish. So we just turn to the second term, and we have the derivative of 2r dr plus the derivative of the second term, which is this one by this formula here. And so to just sum up, the condition that phi c is closed is equivalent to say that u cube dot is equal to 3/2 uv squared, and uv squared dot is equal to 0. So this is the motivation behind the choice of u and v in the previous slide, in the definition of the Bryan-Salomon G2 structure. And in a similar way, you can compute that d of Hodge star of star phi c is equal to 0 if and only if u square v square dot is equal to 1/2 b to the 4th. And this is just once again a straightforward computation, which is done here. So now I am going to just comment on the fact that it is easy to see that the metric is indeed complete. In fact, if we restrict the Riemannian metric to the fiber of S3 times R4, so we pick a point of S3 and we look at the metric on R4, what we see is this conformally changed metric on R4, which is going to, which has this, for which this integral is infinity, and this implies completeness, because we need infinite length to escape infinity. I know I went very quickly. I went through this proof very quickly, but it's really quite straightforward. There is nothing deep about this theorem. I mean, there is a lot of deep about Bryan-Salomon theorem, but the computations are straightforward. Any question? Okay, so I will then move to the second example of Bryan-Salomon, which is the anti-self dual two forms over either the round sphere or CP2 with a Fubini study metric. So so this is the total space of our manifold, is the anti-self dual two forms of X4, which are the two forms for which Hodge star of omega is equal to minus omega. And this is a 3D vector bundle. Actually, this is not really correct, but it doesn't matter. So the idea of all you need to know about the Bryan-Salomon matrix is that in this context is that this is a 3D vector bundle over a 4-dimensional manifold. So the total space has dimension 7, and it has a Euclidean structure which is induced from the metric on X4, and a connection which is induced from the Levi-Civita connection. So once again, we are with a vector bundle with a connection. We can construct the horizontal and the vertical one forms. So there is type here. But so once again, we take a local oriented orthonormal frame on X4, and to it we can construct the anti-self-dual one forms, omega 1, omega 2, and omega 3. And so these are given by B0 wedge B1 minus B2 wedge B3, or B0 wedge B2 minus B3 wedge B1, and B0 wedge B3 minus B1 wedge B2. So this is a local orthogonal trivialization of the anti-self-dual bundle of X4, and so we can find the parameterization of A1, A2, and A3. Now, the geometry of X4, so we picked some very specific four-dimensional manifolds, and these are going to tell us that with two equationals. So the first one is the connection matrix of induced connection on this bundle, and you have these the first equation here, and the second equation is telling us that X4 is a self-dual Einstein-Fermi manifold with scalar curvature equal to 12K. And so this is the reason why we are picking S4 with a round metric or CP2 with a Fubini-Studi metric, because we will need this equation to be true, and S4 with a round metric and CP2 with Fubini-Studi metric are the only such four-dimensional manifolds. Okay. Now, as above, we can construct the vertical one forms as dA plus rho dot A, and these are given by C1 equal to dA1 minus 2A2 rho 3 plus 2A3 rho 2, and C2 and C3 similarly. And the horizontal one forms are given by the horizontal part of the pullback of the local frame B0, B1, B2, B3. So again, we can construct similarly a G2 structure. We pick R3 to be the distance from the zero section, and we assume that the scalar curvature, the scalar curvature is 1. So U and V are just going to be two functions that solve these differential equations, and the G2 structure is defined in the same way, but now we have a three-dimensional, a rank-free vector bundle over four manifolds. So the role of the horizontal space and the vertical space is going to be exchanged. So the free form is going to be U cubed times the volume of the vertical space plus UV squared, this mixed term here. And similarly, as above, we get an induced metric, and the Hodge star of phi is with this form here. So differently to the previous case where phi is globally defined because S3 is parallelizable and the bundle is trivial, this time phi c is only locally defined a priori, and you can see a proof of why the free form is globally defined on Brian and Salmon original paper. So what Brian and Salmon proven was that such a free manifold is complete with holonomy G2, and the automorphism group is SO5 or SE3. And SO5 is just the lift of a standard action on S4, and SE3 is the lift of a standard action on CP2. So as an exercise, I do recommend you to maybe give it a go and see and prove that that phi is a closed and co-closed threefold. So the last Brian Solomon example is the one on spin 7, and if you don't know what a spin manifold is or what is a spinor bundle, don't you worry. We will not really going to need much. All you need is to know that S4 is just the constant sectional curvature manifold that you all are familiar with, and this is the negative spinor bundle of S4 is a vector bundle which is constructed by the associated bundle, this associated bundle here. And this associated bundle is given by the spin structure of S4, which is the double lift of the frame bundle, and we have a natural representation, which is this one here. But what you really need to know is that, as in the previous case, the negative spinor bundle of S4 is a 4-dimensional bundle with an Euclidean structure induced from the round metric, and the connection which is compatible with the induced Levi-Civita connection, and this is the so-called spin connection. Okay, so as above, we pick a local orthonormal frame for our round sphere, and sigma 0, sigma 1, sigma 2, sigma 3, a local orthonormal frame of the negative spinor bundle of S4. And this local orthonormal frame is induced directly from the local orthonormal frame of S4. So we also have local coordinates, so in the sense that each section is parameterized by A0, A1, A2, A3, and this local orthonormal frame. And using spin geometry, you can see that the natural compatible connection has the following form here, which should remind you of the connection on the spinor bundle of S3. And rho 1, rho 2, rho 3 are, as in lambda 2 minus S4, the one satisfying this equation here. It doesn't really matter too much about these explicit forms. All I want you to know is that this is very explicit, and you can really work out everything given a local orthonormal frame of your choice. So as always, we have a connection on a vector bundle, so we can construct the vertical one forms and the horizontal one forms, and these are once again dA plus rho dot A for the vertical one forms, which in this case have this form here, and the horizontal one forms are just given by B0, B1, B2, B3. Pull back to the total space. And so the spin 7 structure that one can construct are essentially as the one given above. So we pick R squared to be the distance from the zero section, and UV to be some function satisfying differential equations, ordinary differential equations, and the polar form, the spin 7 structure that we have is given by, as above, we see R8 in this case as 2 copies of R4, and each copy of R4 is going to correspond to the horizontal space or the vertical space, up to a conformal factor U or V. And the induced metric is, as in the previous case, is just a conformal change of metric on the horizontal space plus a conformal change of metric of the vertical space. Any question about the spin 7 structure? Okay, so if everything is clear or too confusing, so that you don't have questions, I'll move forward.
Sorry, may I ask Federico, the conformal factor, is it accidentally conformal or is it a requirement that it is conformal?
So it's just the ansatz they give. It's this one. So they want to construct another way to see this is a homogeneity one construction. So you pick your factors and you scale them with some function which satisfies some ODE, and they need to be positive. So are you asking me why it is positive, the functions U of V, or
Yes.
So okay, yeah, the point is that when the function is negative, this free form stop inducing a Riemannian metric. So this full form, sorry. And so the metric becomes incomplete, essentially, when the functions explodes too fast or becomes negative. That makes sense. Does it make sense? Okay.
Okay,
So thank you for your question. So if these make sense, now I can just say that once again, this full form is a priori not globally defined, and you should check out Brian and Salomon original paper for a proof of why this is a global definition. And the theorem is once again that such a dimensional manifold with a full form is a complete manifold with holonomy equal to spin 7, and they compute the automorphism group to be sp2 times sp1, where sp2 acts on is the double lift of the SF5 action on S4, and sp1 acts on the fiber. So this is just a recap and a reminder of the idea of Brian and Salomon. So we have a vector bundle over a k-dimensional manifold over right dimensions, and this vector bundle is Euclidean and with some compatible connection. So the tangent space of the total space of this vector bundle can be decomposed into an horizontal part, which is due to the nature of a connection, and a vertical space, which is just the kernel of a projection, of a differential of a projection map. And this decomposition will play the same role of a decomposition of R7 as R3 plus R4, or R8 as R4 plus R4 that I mentioned in my last lecture. And the metric that we induce is just a conformal change of metric of the horizontal space and the conformal change of metric of the vertical space. Now, if we do this in such a way, you obtain some ordinary differential equations on U and V, and these are the equations that we need to satisfy, that we satisfy and that we solve them, and these are the answers. So I guess this kind of answers again the question that Yannis posed, I hope. Okay, now I'm going to take a detour on group actions and manifolds. This is just because yesterday I meant to be quicker than I was. I wanted to cover this yesterday, but I couldn't. So this is something that for some of you might be very standard. For me, it wasn't. So I guess it's good to have everything reminded once in a while. So the idea is, not the idea, but the setup is that we have a compact connected Lie group with some Lie algebra G and a smooth manifold M. and we want to define a group action on my manifold as a Lie group homomorphism. So we have our Lie group, and we have a Lie group homomorphism into the diffeomorphism group of M. And this induces a smooth map, which is just the obvious map defined as follow. And I will always denote G dot P as the action of G on the element P of my manifold. Now, a Lie group actions will induce also a Lie algebra action, which for me is a Lie algebra homomorphism from the Lie algebra of my Lie group G into the space of differential forms of my manifold, and we will often identify G with its image, and we call such vector as the vector fields that are the generators of a group action. So this induction, so the fact that the Lie group action induces a Lie algebra action can be seen explicitly. In fact, this is the formula that we have. So for every point P in M, we take the derivative in zero of, so the exponential map of the Lie group G gives us a one parameter family of elements of G, which acts on the point P. And so this gives a curve in M, and we take the derivative as zero. And this is the definition of vector fields for me at least. Another interesting observation is that, yes, a Lie group action induces a Lie algebra action, but conversely, you can recover a local Lie group action through your Lie algebra action. But this won't really matter too much. What matters is that this is more of a proposition than a definition, but given a Lie group action, a Lie group action on M, we can construct a closed embedded manifold, which is the orbit. So the orbit of a compact Lie group is an embedded manifold, and the orbit space is going to be denoted by M over G. And this is just the space of orbits of my group action. Of course, you are familiar with orbits, and you know that orbits are related to stabilizers somehow. And so here is the definition of a stabilizer, GP, the stabilizer of the Lie group action at a point P. And these, in the case of our interest, so for G that is a compact Lie group, every stabilizer is a compact Lie subgroup. And of course, you're all familiar with standard group action. So when I say that we have a free action, it means that the stabilizer is always the identity, effective if the Lie group homomorphism is actually a monomorphism, so if it's injective, and transitive if the space of orbits is just 1 point. Are you all okay and familiar with this? Can I move forward to the main theorems that I want to say about group actions of manifolds? Okay, then so these are the main theorems that I would like to recall. So the first one is this Lie's theorem, and essentially it kind of says that the local geometry near a fixed orbit is determined by algebra. So given a point in my manifold, and N to be the vector space, so the vector space which is normal to the orbit at the point P, we can construct an associated bundle where GP is the stabilizer of P acting on G in the usual way by the left, and on N by in the usual way. So is the Lie's action. And what it is true is that such an associated bundle is G equivalently diffeomorphic to the normal bundle of the orbit. So a local neighborhood of my orbit is completely determined by this associated bundle, which in turn is determined by a representation. So is an algebraic object. The second main theorem that I would like to mention is about the certification theorem. So essentially, because of this equation here, of this lemma here, for every orbit, there exists a unique conjugacy class of subgroups of my Lie group. And these so gives us these submanifolds of my manifolds, which are the points with the same, which have the same stabilizer in the same conjugacy class. And this in turn gives us a decomposition of my manifold into orbit type here, into orbit types. So my manifold decomposes as the union over all the possible subgroups or conjugacy classes, and the same holds for the orbit space. These are stratifications in the sense that they're locally finite and ordered, and each of a stratum is a smooth embedded manifold, and the projection is a fiber bundle of fiber G over H. The last theorem before I move to, I'm going to be just 10 minutes over time, but the last theorem is the principal orbit type theorem, which says that there is one stratum that is more important than the other. So if M is connected, then there exists a unique conjugacy class, which is the principal stabilizer class, which is a subgroup of all the stabilizers up to conjugacy, and the induced submanifold and P, the stratum induced by this principal stabilizer, is open, dense, and connected both in the manifold and in the orbit space. So the upshot of these is that the above splitting has one stratum which is more important than other and takes most of the manifold. And this is just notation about singular orbits and exceptional orbits. So the remaining of the manifold is either a singular orbit if the stabilizer has bigger dimension than the dimension of the principal stabilizer, or it is an exceptional orbit if the stabilizer has the same dimension as the principal stabilizer. So I know I went through this very quickly, and I apologize for this, but I really needed to cover, I think, some of the material here. Do you have any questions about this? Well, if not, I will conclude by just mentioning and giving a brief description of the Foscolo-Haskins notion manifolds. So this is a non-standard terminology. Usually in literature, you will see them as A7, B7, and C7 manifolds. And these are the recently constructed G2 manifolds with symmetry SE2 times C1. So first, we have the setup is a G2 manifold with holonomy, with cohomogeneity one action of SE2 times SE2. So this means by the splitting theorem that my manifold kind of looks like here, like this. So the orbit space is a half line, and so my manifold will look like a interval times a discrete quotient of SU2 times SU2, and one singular orbit, which is the one in blue here, which will look like SU2 times SU2 over some subgroup of SU2 times SU2. So by the orbit type stratification theorem, the geometry of M7 as a differentiable manifold is characterized by two subgroups that are the principal stabilizer and the stabilizer of a singular set. So it is essentially written down what I meant before. Now this is going to be a subgroup of SU2 times SU2 that is going to be crucial in the first Colohaski-Nordstrom construction. It doesn't really matter here, but just remember that this is a U1 embedded in SU2 times SU2, and this depends on two parameters, M and N, which are coprime numbers. So in the case of interest for the first Colohaski-Nordstrom construction, the subgroups K0 and K are either this KMN and KMN intersected with K2 minus 2, this is the first case, or the diagonal SU2 for K and K0 trivial, or SU2 times the identity and K0 trivial. So these are going to be the K0 and K in the construction. Now, the G2 structure that I defined on the principal part, which I told you looks like SU2 times SU2 over some discrete subgroup of SU2 times SU2 times an interval. So on the interval is going to be parameterized by dt, for instance, and SU2 times SU2, we have the coframe of left invariant one forms that I mentioned before for the Bryan and Salomon manifold. On such an MP, I can define a free form Phi for some constant C1, C2 in R, which is given by this formula here. And what it turns out is that this is obviously closed, and it is torsion-free if and only if A and B are two functions satisfying some ODEs. It turns out also that there is always a local solution due to H'ing, and VC is invariant under the action of SU2 squared times U1 that acts on V space MP like here. So the problem to define a global G2 structure in such a way is that we have a local solution of the ODE, and when this local solution extends to a global solution, and the answer to the question is yes, the implicit ODE, so yes, and this is done by an implicit ODE study and the singular initial value problem. So the theorem that Foscolo, Haskins, and Nordstrom proven is the following. So in all cases of interest 1 and 2 above, M7 admits a one-parameter family of complete non-compact G2 manifolds with full holonomy, and the same holds for every Mn coprime in the case 3. And finally, all complete simply connected G2 manifolds with SU2 squared times U1 symmetry are constructed in this way. So, for instance, since I told you that Bryan and Salomon had SU2 cube symmetry, it is an element of the FHN manifolds, and these are the data that you need to check that. So this is really what I wanted to say today. I went super fast, so please ask me questions if you want. And yeah, this is it. Thank you for your attention.
All right, thank you very much. So, any questions? All right, thanks, Federico.